Okay, let's look at the lemma 13.2. This lemma says that let X be a topological space. Suppose that C is a collection of open sets of X such that for each open set U of X and each X in U, there is an element C of the collection C such that X is an element of the subset subset C, and the C is a subset of the open set U. Then the collection C is the basis for the topology of X. This lemma means that if there is a collection, we call it C, like this, and this collection is on the topological space X and with topology T. Then it has like this collection C has the this property. So for each open set U of X and each X in U, there is an element C of the collection C such that X is inside of the C is a subset of U. So this means for any open set U is from the topology T, and inside of the X for any U, and for any X in U, then there is an element C, the C from the collection C, and this C contains the point X, and this C is inside this open set U. So if the collection C is true, like if we can always find such C from the collection C for all the open sets U inside the topological space, and for all elements in the open set U, then we see that this collection C is a basis. C is a basis of this topological space XT, which means C generates the T on the X. Okay, so in order to prove this lemma, we need to prove this C generates the T. So like we can do the proof in two steps. In the first step, we can prove that the collection C is a basis of some topology on the X. Maybe it's not the T, maybe it's a different topology. So at least C is a basis of a T prime on X. So C should be a basis. And then, because we want to prove that C is a basis of the T, so we need to prove T prime is actually same as a T. So with those two steps, we can prove this lemma. Okay, let's do it. So let's delete this first. Okay, proof. So for the first step, we need to prove C is a basis. And because we don't have too many tools to do that, so we can use the definition of a basis to prove the collection C is a basis. And because in the definition of basis, there are two properties. So if we want to prove C is a basis, we need to verify if C satisfies the two properties or not. So here we check the two properties with this collection C. And the first property of the basis is like this: for any X, in the set X, we can always find an we can always find a C from the collection C, such that X belongs to this C. So this is the first property. The collection C should be satisfied. So why this is true? So we can do this. The set X, big X, the set X, it is the entire set. So according to the definition of topology, the X should be in the topology T, and this means X is an open set. So X is an open set, and for the collection C, we have this property here. So this property is about the open set of X, and we can do something for the open sets in the X. And now because X is open set, so we can use this X to replace the open set U here. And let's see what can we get. So if we replace U by X, we can get for the open set X of X, and for each X in the X, for each X in the X, there is an element C of the collection C. There is a C from the collection C, such that X belongs to this C, and this C is a subset of, not U, of the X. So we can see, actually we don't need this part. So we can see this result is actually what we need here is same as this property here. So the X is inside a element from the collection C. So we like this, we just prove that the C collection C satisfies the first property of the basis. So the first one is proved. How about the second one? The second property is that, like, for any C1, the C2 from the if C is a collection, then C1 and C2 from the basis C, then for any X element in the intersection of C1 and C2, and then we can find another element from the collection C, such that X is inside this C3, and this C3 is a subset of the intersection area. So this is a second property. The collection C should be satisfied. And let's prove this. So we can see C1 and C2 are the elements of the collection C. And because the collection C is a collection of open sets of X, so C1 and C2 should also be open sets. So C1 and C2 are open. And it also means C1 and C2 belongs to the topology T, because this open means it is open inside the under the topology T, not under the topology T prime. So C1 and C2 should be elements of T. And then because C1 and C2 are elements of T, then the intersection of C1 and C2 should also in T, according to the definition of topology. Okay, so C1 and C, the intersection is the element of T, and it means the intersection is open. Okay, and then because this intersection is open, we can again replace the U in this statement, in this property, with this intersection C1 and C2, and see what can we get. So for this open set, and for each x inside this open set U, which is the intersection C1 and C2, there is an element C from the collection C such that X is in C and C is a subset of U, which is the intersection of C1 and C2. Okay, so we can see this result is same as we want here, right? So we just need to replace the C with the C3, then we get the property, the second property of the basis. So the collection C also satisfies the second property of the basis. So according to those two properties, we can see that the collection C is a basis on X. Basis on X. Okay. Okay, we have proved this first step, and for the second step, we need to prove that the T prime, which is the T prime is the topology generated by the collection C, and so T prime should equal to the T. So in order to prove two collection or two sets are equal to each other, we can prove first T prime is a subset of the T, and then we prove T is a subset of T prime, then they should be equal to each other. So we first can prove T prime is a subset of T, and then we can prove T is a subset of T prime. Okay, let's prove this one. So in order to prove T prime is a subset of T, we need to prove for any element, maybe we call it V from T prime, we need to prove V is also in T. Then we can say T prime is a subset of T. According to the results we get before, we know that the elements of the topology are the union of the basis elements from the basis. And here, because the V is an element of the topology T prime generated by the C, so U should be the union of the basis elements from the basis C. So U should equal to the union of all the some Ci from the collection C, like this. So this is true for all the V from the T prime. And then we know that the collection C, or the basis C, is a collection of open sets of X. So it means C are open, and it also means C from T So we can have this. And then according to the definition of topology, because all the Ci are from the topology T, so the union of them should also be an element of the T. So the union of Ci from should also from T. And this just means the V is from T as we want. So we proved this first step. The T prime is a subset of T. Okay, and then we need to prove the second part. The T is a subset of T prime, like this. So in order to prove this, similarly, we need to prove for any U from the topology T, we need to prove that U is also an element of T prime. Okay, in order to prove this, because we need to prove some subset of X to be in the topology T prime, one way we can do that is use the basis. The basis is C, which generates the T prime to check if the U should be in T prime or not, as we did before, right? So we use C to check U, and the way we check the subset U is open or not is we find all the elements in the U, and we need to find C from the collection C, such that the X is inside this C and this C is inside the subset U. Then, if this is true, then we can prove U is inside the T prime. And this is obviously true because the U is from the topology T, so U is open. And so since U is open, so we can use this property, and it just says for any X in U, we can find the element C, and we have this property, this relationship. C is in C, and C is a subset of U, which is identical to what we want here, as C is element of X is the element of C, and C is a subset of U. So this is proved according to the property of connection C, and then we just proved because this is true, then we prove that U is the element of T prime, and since this is true, we proved that T belongs to T prime. Okay, so we proved this relationship, and with those two results, we can see that T prime is equal to T, and so we proved this, and because we proved those two steps, so we can see that the C is a basis of T under T prime, and we can directly say T here on X, which we proved that this lemma.